Please welcome co-CEO and co-founder, Christoph Gebald. Christoph, the floor is yours.
I'm so grateful to see so many of you coming, and I know many traveled for a very long distance, and it's night or a different time of the day. And I'd like to welcome you for this year's summit. Well, we're all meeting here because we're interested in direct air capture. And my interest and fascination for this topic goes back 16 years. And when I reflected this journey the past 16 years, I noticed a couple of things. The first one, I noticed nobody on Earth logged more mileage on researching and pushing commercial deployment of air capture than I did, which made me feel very old. So, jokes aside, when I reflected the last 16 years, what I noticed is that the topic of air capture proceeds in widening circles. When Jan and I started 16 years ago, it was like day in and day out. Everything we did was technology development. The output of the global air capture industry at that time was 1 patent application per year in 2007. In 2022, this number increased to 100. That's the same rate as wind energy and solar had in the late 1990s or 2000. And we all know what happened thereafter. The business model is shaping up. Only in the last month, in May 2023, more than $200 million have been committed to carbon dioxide removal services. And we're proud to hear from some of the champions on the market buying carbon removal. No, nothing of that would happen without a powerful team. Since we last met here at the Air Capture Summit, and today, Climeworks has been growing by 60%, and today we have more than 300 Climeworkers working on our mission. End of last year, we provided the world's first third-party verified carbon dioxide removal to the market, and with that, we are advocating for high-quality carbon removal, and we're setting the stage for policies to develop. And on a very big picture, in the last 12 months, on the policy side, substantial development happens. The European Commission developed a framework how to certify high-quality permanent carbon removal. And in the United States, with the Inflation Reduction Act, we're seeing tax credits of $180 for air capture. And through the Department of Energy DACA program, $3.5 billion are in the room for deployment of air capture. Now, all of this is impressive development, and that's a strong pillar in working against climate change. But not only that, it's also the start of a new industry, and it creates a new job. And from our side, we, like air capture, makes the living for 300 people and 300 families. So air capture is real, and it is here to stay. Now, looking to the future, Bloomberg gave some numbers where the carbon removal industry could go. And they say, in 15 years from now, the market size of carbon removal can reach $1 trillion per year, which is very substantial acceleration from where we are today. Now, where are we today? Looking at a study published recently by Shell and the Boston Consulting Group, between 2015 and 2021, of all credits sold on the market, only 20% have been removals. Looking at the half time between today and the 15 years mentioned by Bloomberg, it's 2030. Also, they're looking at how will the market shape up, and they're, again, consulting a BCG report. The majority of portfolios buying carbon credits at that time will have a share of more than 60% of carbon removals in their portfolio. Notable, 7% of all portfolios will run purely on carbon removals. This is the same takeaways from a different source. This graph is extracted from the Oxford Principles. Don't take the numbers as exact, like take it as directional. What it says, it's exactly the same. In 2020, 3 years back, carbon credit portfolios, largely avoidance and some short-lived removals. In 2023 to 2025, like mid of this decade, we see high-quality, long durations removals to pick up, They're in the low double-digit percentage added to portfolios. That's the lower part of this curve, the dark blue part. By 2030, we have roughly a third of that in the portfolios. And by the point we reach net zero, which is assumed to be the case in 2050 on this graph here, the only thing as a credit that's to be allowed is high-quality, permanent carbon removal. Now, putting all of this together, this means very strong growth ahead for the carbon removal industry. And direct air capture will play a very critical role and a crucial role in scaling this market. Why? Because air capture can fulfill very important criteria. The first one, additionality doesn't get any easier than for air capture. Like, if we don't build plants and we don't run it, it's not happening. Like, again, additionality doesn't get any easier than that. Same on the measurement, reporting, and verification side, MRV. Other approaches have a hard time to have the same MRV as air capture has. We can measure exactly how much CO2 we capture, how much we store in the ground, what the environmental impact is that we have that we need to subtract from the other two. And lastly, we don't need arable land. And the importance of this point can't be stressed enough. Some people say air capture can't be scaled to meaningful scales because it requires too much energy. In my point of view, this conclusion makes no sense. The world primary energy demand is 1% of the energy supplied by the sun to the planet, excluding water, just focusing on land mass, right? So again, let's take a crazy extreme scenario. Assume we were to capture 40 to 50 gigatons of carbon dioxide from the air with air capture. This would require the same amount of energy as humanity is using today, the world primary energy use, 170,000 terawatt hours. Or in other words, 1% of the energy the sun is supplying. Is it challenging? Yes. It's clearly a multi-decade, multi-trillion-dollar effort to get there. Is it right to conclude air capture requires too much energy? No, in my point of view, not. And this is why not requiring arable land, which you can take as a synonym for energy, is such an important thing. And all of this translates into this graphic, which is extracted from the IPCC report, which gives the scaling potential of different CDR, carbon dioxide removal approaches. And in the low line, you see direct air capture with a lower bracket of 5 gigatons running all the way up to 40 gigatons. And, well, I hope we never will use the right bracket and we have reduction efforts so we can focus on the lower brackets. But as the game ahead of us is a pure volume game, the importance of scaling and scaling potential can't be stressed enough. Now, re-looping to the beginning, the widening circles. I'm sometimes asking myself whether in 16 years from now, we think about what we're discussing today and the output we're having today as the one patent in 2007. Probably it won't take 16 years, maybe only 3 years with the pace we're going. And I'm asking myself, what is beyond what we're currently thinking about? And once I've shown our plant close to Zurich to a person who I very much admire, and we talked about air capture and his vision why air capture exists and why it's so important. And he told me, in his point of view, air capture is so important because it can be a tool for the developed countries to pay back the debt it owns to the developing countries. And that adds another very important layer on a social and emotional level to solving the climate crisis. And solving the climate crisis is exactly what we are passionate about and what we care about, and this is why we commit to high-quality carbon removal. Now, all of this is integrated in this plant. This is doing the job. That's the world's only plant currently capturing CO2 permanently from the air with third-party verification.
Well, this is indeed a very beautiful picture, right? There's just one detail I would like to add here. The reality when operating that plant and many others out there in the field might, at many days, rather look like this. So with that, also very warm welcome from my end to the 2023 Direct Air Capture Summit. And thanks to Christoph for giving us a time warp of the developments in CDR, carbon dioxide removal, over the past 16 years, and in particular, the incredible momentum that we've picked up over the past 2 years. Thanks. Now, when zooming into what is it about actually doing direct air capture, I would like to share 3 principles or 3 thoughts, 3 topics with you that we believe are particularly important when predicting the scale-up and in particular the cost down or the cost development of direct air capture. And on top of only listening to us, to myself, what I recommend to all of you when thinking about that type of infrastructure and how to scale that and how to build that out is talk to the big industrials. Talk to those people who've built that type of infrastructure over the past century, not only the past couple of years. Talk to oil and gas, talk to the gas processing companies, and talk to big construction companies who've done that for 100 years, who've built those plants, and who've operated them. And what you'll probably find out in these discussions is that when you look at this picture and think, well, this looks quite challenging, but maybe that was just a bad pick of a first location, being in Iceland with harsh winter conditions and so on, you might figure out, and those people might tell you, well, you can take away the snow, but you can exchange it for a hurricane, or you can exchange it for a sandstorm, or just a lot of salt in the air. And at almost any location where you will build those plants, you will have at least one of them. And that makes it really, really challenging. Now, with that, topic number 1. To successfully scale stuff like that, development needs to be driven from the field. So those people who will actually carry the majority of the work to de-risk those type of technologies, to make them more efficient, to make them more available, more performant, to scale them up, those will be the field engineers and the field operators being out there and making those plants alive. And those people will typically be faced with topics like this. Those are all original pictures from our Orca plant up in Iceland from the first year of operation. If you look at them, you might think, well, they are actually trivial. Those are problems the world has already solved. That's not an issue. And you look at them and you might think, well, those are trivial problems. They just picked the wrong material there for the design. Nevertheless, those type of problems, they were responsible for the vast majority of downtime, non-performance or underperformance or under-availability of the plant over the first year. That's what it is really about. And also, just to give one example, if you zoom in there, it is not as trivial as it looks like. Again, if you look at the left-hand side picture, you might think, well, they just picked the wrong material. It is a corrosive atmosphere, and they picked something wrong. But you know, deployment in the field, it's not only about design. It's about multiple factors, for example, also supply chain. And in fact, this left-hand side picture is a result of a conscious decision, of a compromise between wanting to install a new type of design very, very quickly in the field, where, on the other hand, the lead time or the delivery time of the appropriate stainless steel part was more than 20 weeks. So just to give an example. So those are the topics that those folks are dealing with. Topic number 2, I chose a particularly boring title, which is nomenclature. Now, it is a very important one, though, because it happens again and again that 2 people talk about, in particular, a new industry, a new type of deployed technology like direct air capture. They think they talk about the same thing, but their numbers are actually a factor of 2 or 3 off. Not 20 or 30%, but a factor of 2 or 3, because they are not talking the same things. And just to give one example, one tool that we have introduced at Climeworks and that I invite all of you to use when thinking in this space, and not only relevant to direct air capture, it is what we call the capacity waterfall. So it's a lot of details here. You don't need to look into all of that now, but just to give you the general concept, what is shown here is when we walk from the left-hand side to the right-hand side, we show what happens between the actual design nameplate capacity of a plant and then the actual tonnage of carbon dioxide removal that can be sold to a customer. And there are a couple of losses in between that will happen generally to all type of technology. So to name a few examples, the plant is never every time available. So you have to subtract. If you have design capacity, it will not run for 8,760 hours per year, which is the number of hours in a year. So you go down there. You will not recover all the CO2. There will be losses in there. People who work in CCS, carbon capture and storage, they know that very well. You will never be able to recover all of the CO2 that you have captured. And then maybe most importantly, here on the right-hand side, we have to think about net carbon removed. So we have to subtract gray emissions. So whatever the plant emits during this construction phase, during the operation, during the energy, we have to subtract that. Sounds trivial to many of you, but isn't if you look at the numbers that are out there in the field. And if you look at that as a whole, just as an example, if the nameplate capacity of the Orca plant, that's the left-hand side bar, is 4,000 tons of CO2 captured from the air every year, then it's a real lot of hard work required to be able to sell 3,000 tons of net CDR to a customer at the end of the year. And there's another reason why I particularly like that graph. I think it's something really useful and handy. You know, there's a lot of dynamic in the field currently. A lot of innovation is happening, which is great. A lot of inventions coming up, a lot of laboratory scale developments. And from time to time, it happens to us, to me these days, that someone comes across and says, hey, I have this really new direct air capture technology. It's a $100 per ton technology. What do you think about that? How does it compare to other technologies that are out there? And what might typically happen is, well, I would ask two things. First, what are the dollars? We'll get to that in a minute. And the other thing I would do is I'll pull up this chart and walk through that chart together with that person and look at what it's actually about. And typically what we might end up is the finding that, well, maybe we're actually dealing with a $250 per ton technology here, if and only if we can overcome those 20 challenges ahead of us. Some of them we don't even know today. So building stuff like that is hard. And so we should at least get our numbers right. That is something that I want to make sure that as a whole domain, we can get more scrutiny and we can get better. And I think that that'll help all of us walking forward. Now, topic number 3, the million-dollar question, what about cost? And again, here we have to be careful with nomenclature and talk about the right thing. So when we talk about cost, that is a very simple way of representing what we mean. So a cost per ton on the one hand, well, simple things everyone knows is CapEx and OpEx, which is typically together known as cost of goods sold, the cost. But then we should also add an overhead. We should add SG&A. We should add margin. So that would be the total cost divided by the tons of CDR produced, so divided by the net CDR. Again, if you get that one by 30% off and that one by 40% off, you're a factor of 2 off, just roughly. So that goes kind of hand in hand with the previous one. And before sharing what our outlook and view on the cost of direct air capture is, I'll just want to show you this exemplary curve here, which is taken from the photovoltaics industry. And that's typically referred to as the so-called cost mountain. So what you see here is how the cost first estimates and then later demonstrated costs have developed over the decades, divided into 4 different phases. And what you observe, and that was in the 1950s, you start with R&D-based cost estimates, which are typically ambitious, not too low, but also not too high either. Then you start implementing. So before you can start off reducing costs, you actually do have to walk up the cost mountain, walk up the cost curve. That is when you discover all the unknown unknowns. So you walk up, and you actually never know if you have really reached the top up until you are somewhere down there. That's the tricky part of it. Well, at a certain point, you start with the deployment, you optimize, you make things better, and you go into maturation of the technology by maturation of the supply chain, making that more mature, scaling up, building much, much, much more, 10x, 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 and then is the time when you really go down. Now, obviously, I'll show a very similar graph for the direct air capture space. And again, I don't want to go into super detailed numbers here, but just show you the big picture, how we perceive the space today. If we start on the left-hand side, $600 to $800 per ton, that's where our early first estimates were when we built our first plans. There was a report back in 2011 stating that number. And we have walked up in the meantime. With current plans in the field, we are rather beyond the 1,000. Is that representative for long-term deployment? No, it is probably not, because we are relatively small scale. It's all first of its kind, but that's where we are today. And when we think about deployment and maturation, we think about the timescales of 2030 and 2050, with a big step change that is going to happen in this decade, in our opinion, going down to a range of 400 to 700 on our end. And then eventually, when we talk about 2050, but not in 10 years from now, 2050, we put a range of 100 to 300 down here. We'll learn more about that. There will be speakers later who will say this is a very challenging range. There will be other speakers who might be more progressive on that or in that range. But what is common to all is that we have large ranges everywhere. And that is not due to unknowns, which are there as well, but it also is really due to the fact that wherever we build plants, what are the boundary conditions? Do we pay 20 cents per kilowatt hour or do we pay 80 cents per kilowatt hour of energy? How much do we pay for sequestration? What's the cost of labor? All these factors will give you almost a plus minus 50% on the overall cost. So that is something that we should keep in mind. If we think about these two steps, just 2 words on why I said there will be a big step change this year. Those of you who were here last year at the Direct Air Capture Summit, you remember those analogies I'd like to explain about how tricky it is to take CO2 out of the air. You have to move a lot amount of air. That means also that you cannot make a direct air capture system extremely small. There are just physical limits, so you cannot make it 10 times smaller. That's just physically not possible, but you can make it 2 times smaller, and that's something that we are working on. So we think we can compact the systems by a factor of 2, and at the same time halve the energy consumption. So those are by a next generation of sorbent materials, next generation of module design. This is what we will achieve, and that's what will lead us there. Over there, we will need not only one company, not only a handful of companies, but we will need the whole supply chain. We will need maturation on the supply chain side. We need maturation also on the project development side. We need low energy and low cost and low carbon energy sources. We need cheap storage of CO2. So a lot has to happen down there around the core technology of direct air capture. And just very briefly, when we discuss the step between here and there, what we do apply is learning rates. We're running many, many scenarios. And what we find is that for the direct air capture modeling, we use learning rates at the range of 8 to 10%, broken down to the different components of a direct air capture system. We believe on the sorbent side, on the chemical technology side, there is a lot to learn. On other more mature topics, there is maybe less to learn. And when we compare this to other types of technologies, we see this could be even a bit conservative. If we look at very modular systems like PV, we saw learning rates of up to 20%. If we look at more bulky systems which are not that modular, like geothermal or conventional process technology, then we are at 5 to 8%. So that's where we park there in the middle, because a big DAC plant it has components of both of them. Now, going back to my very first principle, in order to do all this, what we need to do, first and foremost, is building stuff in the field. Another beautiful picture here, that is a 10x scale-up of the Orca plant. That is the mammoth plant that is up in construction in Iceland as we currently speak, with the main goal of keeping very fast iteration and learning cycles of our technology. So currently, what we are trying to do is, within every winter season in Iceland, deploy a new generation of parts of the technology to learn and get stuff more mature. In order to enable this, we need the market, and we'll hear a lot more about that. Just exemplarily here, a statement that we don't need the whole market to buy direct air capture for any net zero targets. That's not possible. That's clear. There's an exemplary portfolio by the World Economic Forum saying we have 40, 40, and 20% being the engineered solution. So this is something that can very well do the job. And on a more broadly picture, what do we need? We need the offtake. We need, on the project development side, energy and storage. We need deployed technology. And I'm not saying when I speak about deployment that technology is not important. We are at the heart a technology company. We probably have the biggest technology team working in DAC currently. More than 100 out of 350 people are working on the fundamentals, on sorbent material, on pore sizes, on functionalization, on materials. That is important. But what they do has to be driven from deployment and from the field. And we do need financing both on the public and on the private side. And with that, I'll finish for once, not with real pictures, but with images made by the computers. we're not talking about 10 NICS plants being built next year, but what you can expect by the end of this decade from our side is a handful of direct air capture hubs at the scale of 1 million tons per year. And you see a few pictures how this could look like. This is what is in our funnel today, and we are working on, and you'll learn more about that in the next summits to come. I'm pretty confident about that. With that, thank you very much.